Welcome everyone to the next seminar from our mini symposium. Thank you, the organizer, for organizing this very nice symposium and for the invitation. And I would like to formalize mathematically the experimental protocol that Claudia told you before, and also formalize the mathematical model that we use to formalize all this problem. And in the end, I will speak a little bit about the model selection procedure that we use in this class of model. So the motivation is this experimental protocol that Claudia told you before. So we have some stochastic stimuli, and we expose some volunteer to this stochastic stimuli while we record some behavioral or physiological answer. In my case today, I will speak about physiological answers. Okay, so I will speak in particular in the case when we have some auditory stimuli, and the answer, the physiological answer that we are recording are electroencephalographic data, which basically record the electrical activity from the brain. In the mathematical point of view, we have some functions as answer. Okay. So we have strong bits, weak bits, and silent units, and these are our unit of stimuli. If you want to generate some sample, some stochastic sample from this, one way of doing is starting from the deterministic sequence 2, 1, 1, 2, 1, 1, 2, 1, 1. You can erase each one by a 0, and then we will have something like that. So, for instance, in the deterministic case, the stimuli will be something 2 ta ta 2 ta ta 2 ta ta. And when we erase some of the weak bits, like in this case is here, we will have something like 2 ta 2 ta ta 2 2 ta ta 2 ta 2. Okay, so this will be basically the kind of stimuli that we expose to our volunteers. Okay, and this is one way of generating this kind of stochastic stimuli. If you want to generate step by step this stochastic stimuli or stochastic sequence, you can do it in the following way. So if you want to know what is happening in the xn step, and I don't give you any kind of hint, the best you can do is guess, right? But if I tell you that actually in the step n minus 1, the last stimuli was a strong bit, or a 2 in our numerical sequence, then in this case, you know that you have, for instance, so we are in this situation. So these are our last step, the kind of last step we can have. So the next step, when you saw a 2, a strong bit, is either a 1 with probability 1 minus epsilon, or a 0 with probability epsilon. But in both cases, you know what to expect, right? So you know how to generate, at least in a probabilistic point of view, what is going on in the end step. So here we will have something for this step here, we will have something like that. So the probability of having a 0 after a 2, it's epsilon. The probability of having a 1 after a 2 is 1 minus epsilon. I'm sorry for my cat. Okay, he's singing a lot today. So, but in the other hand, if I tell you that actually in the n minus 1 step, it's a 1, we will have basically two kinds of 1. So either you have a 1, which comes after a 2, and then for this case, we have either a 1 or I don't have any case here. I will put 1 here, and then you can have a 0 here. So if you are in this kind of ones, the ones which comes after a 2, then you can have a 1 with probability 1 minus epsilon and a 0 with probability epsilon. So you are basically in this case. So it's the ones which comes from 2's, right? But you also can have ones, a second type of ones, which comes after a 1. So I have this kind of 1, which is coming from another 1, or these kind of ones which are coming from zeros, right? And in both cases, even those which come from ones or which come after zeros, you will have a 1 or 2 here with probability 1, right? So we either in this case or this case here, we have this kind of behavior. So if you have a 1 followed by a 1, then for sure you have a 2 with probability 1. If you have a 0 for a 1 which come after a 0, you will have a 1 with a 2 with probability 1. Okay, this is the point. So in the end of the day, we have split this guy here in 3 different situations, right? So basically the ones which comes after 2 and the ones which comes after either a 0 or a 1, right? And for each one of these situations, for each one of this kind of ones, we have a different kind of transition probability, okay? And the same will happen if I give you the hint, if I tell you that actually in the time n minus 1, we have a 0. We will have 2 kinds of zeros, the ones which comes after a 2, so this kind here, the blue ones, and we have also the red ones, which are the zeros which are coming after ones or zeros. So for the red ones, we have a 2 with probability 1. So I'm in this situation here. Which one? These ones. So in this case, we have for sure a 2 with probability 1. And for this case, also I will have a 2 in the next step with probability 1. And for the green ones, the blue ones, the 0, these guys here. These guys here, the blue ones, we are in this kind of situation. So we have a 1 with probability 1 minus epsilon, and we can generate a 0 with probability epsilon. So in all of these cases, I have split here in 3 kind of different situations. But doesn't matter which one I'm looking at, and doesn't matter which one is happening at time n or n minus 1, I will be able to generate what is happening in time n if I have, because I have the transition probabilities well defined, okay? So basically we are splitting all the possible path symbols which can happen up to time n in 7 different situations, either finishing in 2, or 2, 1, 1, 1, 0, 1, 2, 0, 1, 0, and 0, 0. So this set here, it's a partition of all possible paths, and for each one of the situations, we have some transition probability associated. So given a path, we associate a context, element of the set, which are called contexts, okay? And once I have a context associated, I can use the transition probability to generate the next step, okay? The formal definition of all these 2 objects that I just speak, the tree and the table with transitions probability, we can formalize it as follows. So suppose we have some string here. So for instance, all this, it's a string U. I don't think you are seeing. I will put it in red. So I will say that V is actually U is a suffix of V if V is bigger in some sense, like V is all this. So this is the present. And U is something is shorter, but shorter in the past, okay? A context tree we can define it as follows. So a context tree for us is something which has 2 basic properties. The first one is the suffix property, which mathematically means the following. No string W, it's a proper suffix of another string, S. What does this mean in our picture, in our hierarchical way of doing the tree? So this is just saying that actually the set that we are using to partition the past is only with the leaves. So I'm not considering in this picture any internal node, only the leaves, okay? This is how we translate the suffix property. And we also need irreducibility. What does this mean in our scheme before? So this means that actually no terminal branch is the only child. This means that when you construct this hierarchical structure, you will not have something like that, for instance. And then a terminal branch with only one child here. Because if I have this kind of situation, I can just prune this branch and actually replace this guy here for us something smaller, which is this one here. And I still have this only leaf property that is the suffix property. So this cannot happen. And the way we define this kind of not accepting this behavior is with this irreducibility. This is something that we have to guarantee in order to have the smallest past possible, okay? So if I have a context tree, now I want to define a context tree model, how I use this tree to generate stochastic samples. So given that I have a context tree model, I will associate for each one of my contexts a transition probability. So I also need some family of transitions probabilities. And I will define some context function CT, which basically at each step will search in your past what is the smallest past possible or the smallest past needed in order to generate in the next step. This is what it's right in here. So what this C function makes is basically find the context W in your tree associated to any kind of past, okay? And then we use this. So C will work here. And once we found the context associated, we will use the transition probability associated to this context to generate the next step, okay? The condition 2 is only saying that this CT is this function is actually found the smallest relevant past, okay? So I cannot look at any smallest past than my context and still have enough information to predict what is to generate the next step. This is what condition 2 is saying. Very quick word about context tree models. They are also called the stochastic chain with memory of variable length and variable length Markov chains. And they were introduced by Hissanin as a universal system of data compression in 1983. Okay, up to now, I have defined our stochastic stimuli, right? Remember that we have here a guy, and then we have some stimuli and some answer. I have defined to you this part. So this is well defined, at least formally defined with the last slide. But I still have to define this, and also I have to define the relation between this and this. And this relation is the model that we introduced in the literature, okay? So in order to define this, we have to basically decide or formalize how these answers depend on the sequence of stimuli. And then we have something like that. Let me erase this quickly. What we are supposing, what we are assuming is the following. Suppose we have xk, xk minus 1, xk minus 2, xk minus 3. And suppose also that up to time k, our context is this guy here. So this green stuff is the relevant part of the past that we need in order to generate the next step in this chain x k plus 1, okay? Our assumption, the the assumption that we are assuming that the brain is doing, or the way we are defining our model, is this green part is also responsible for generating the K answer. Okay, so the law of this K answer will depend on this, only this green part. Okay, then once we generate a next step, K plus 1 step, I have to do it the same. So for this past, I will look at the context associated in the stimuli sequence. So here I will look, for instance, this part of the past, and this will be responsible to generate the next step in my stimuli sequence, but also the answer associated to step K plus 1 in my answer sequence. This means that actually my functions here, my EEG functions, I will put it in green because this is what makes sense. So these functions in this step and the functions in these steps are generated by laws which actually depends on this green part, only this green part, and this one depend only on the red ones, okay? And so on. So now here I can look at the next step. For instance, this is the context, and this will generate the K, this is K1, and this is K2 steps. Okay, so this is the way we define a model where you have answers, and these answers depends not only on the single stimuli at the K time, but also depend on the context associated to this stimuli sequence up to this time. Okay. Formally, how we say that? So the model is called sequence of random objects driven by context-free models. And what we need in order to define this model? Well, the first things is we have some bivariated stochastic chain, right? The stimuli and the answer one. The stimuli one, we are supposing that it's assuming some finite, it's assuming values in some finite alphabet, and yn for us, in this case, are functions, for instance, but could be something else. And the first thing we need is, well, our sequence of stimuli, it's a context-free model with parameters tau and p, and conditioning in the stimuli sequence, the answers are independent. So if I give you all the stimuli sequence, I will decide what is the answer, what is this brain answer in an independent way, okay? And also, I will not need to look at all the past, but only the context associated, okay? So at each step is the way I just make the figure for you. So at each step here, I will figure it out what is the brain is doing by choosing independently from each one, but from each answer, right? But the law are depending on the context associated. So this is coming from the stimuli, right? Giving the sequence of stimuli, I found my context, and given the constant context, I will generate a piece of function, a piece of EEG associated to this context, okay? What we know about context-free models, not the functional one or the bivariated one, only context-free models. We know how to estimate trees. We know estimate trees and actually estimate also the transitions probability. This you can do it using algorithm context or Bayes information criterion. These two here are constant dependent. So you need to choose a constant and then use this to penalize your likelihood, for instance. And then this will be estimation for your tree, but estimation which depends on a constant. And this procedure here can just choose the optimal constant in both procedures here. So if you apply either context, algorithm context and SMC, or BAC and SMC, in the end of the day, you have estimated tree and constant free, okay? This is for context-free models. What we want to do now is, well, we have here a sequence of stimuli, x1, xn. And for this, we know how to estimate a tree. But we use this to stimulate someone, so, right? So as a stimuli to our experiment. And then we have x1, x2, xn as an answer. What we want to define now is how to estimate a tree from this sample, this function. So this is how we can find a tree in this set now. Okay, this is what I will do it now in the time that I still have. So the way we do it is basically with some adaptation of algorithm context and some projective method. So I will start explaining to you what is the algorithm context. Suppose in some way that you know how to construct the biggest tree possible, which makes sense for our stimuli sequence, okay? I'm not defining the biggest tree, but suppose that you have it. Once you have it, what we will do? We will choose one of these terminal branches. So for instance, I'm choosing this red one here. And I will test this branch statistically. I'm not telling you how to test statistically. I'm just saying that I will find a statistical criterion, and I will say that this is my criterion to prune or keep a branch, okay? So I will do it for this branch here, and then I test if I prune or keep, and I will decide if my statistical criterion say prune, I will just cut this branch and put this guy here instead, and then I will do it in the next branch, for instance, this one, okay? And then I will make the same question with my statistical criterion, prune or keep. So in the end, and we will do it up to having tested all branches possible. For instance, if I have some 0, 1, 3, suppose that this is the biggest tree possible, and then I will apply my general algorithm context here. I'm not telling you how to construct the biggest tree, either the statistical criterion. Just suppose that we have something defined, and we will see how the general idea works, okay? So for instance, I prune the first branch, and the second one, and the third one, and then the fourth one, and the next one, and the next, and then I leave this one and cut this guy here. I cut it too. And I keep doing up to the end. So if this is my last tree, what does this mean? That actually I tested this branch, and then I decided to keep it. So I keep it. This one I keep it. This one I keep it. But for instance, these ones I cut it. This one I cut it. This one I cut it. So this is the final result of some general algorithm context, okay? And this is the tree that we have in the end. Notice that my tree in the end is only the leaves, right? We are not taking any internal node. This is just to define how to use the biggest tree. Maybe I will not speak about that. I think I don't have much time yet. So I'll just skip this, and I will go to this projective method. This is our prune or keep criterion, okay? So prune or keep criterion, for suppose we have this biggest tree possible, and then we want to prune or keep some branch. In this case, in particular, I'm choosing this branch here. In our protocol, experimental, for instance. So 0, 1, 2, and 1, 1, 2. What we wanna do? We will find in the sample each time that each one of the sequence appears. So for instance, it's appearing here, 1, 1, 2, 1, 1, 2, 1, 1, 2, and appearing in green here, 0, 1, 2, 0, 1, 2. Each time that this sequence appears, I will cut this part here, this purple part here in the sample, and put it in some set that I'm calling here. Let me do it like that. So this is purple. I will put it in red here. Oops, no, here. I will put in this set, and the green ones, each piece of green part that I'm taking here, I will put in the set. Okay, so I will find in my sample each occurrence of 0, 1, 2 or 1, 1, 2 and take pieces of EG and put in these respective sets. So in the end, what I will have two big sets of functions, right? This y0, 1, 2 and y1, 1, 2. And my statistical criterion to decide to prune or keep the branch will be the following. I will test these two sets. So now I have one set here associated to this guy and another set associated to this guy. And the question that I will do it is statistically, are the law of these two sets equal or not? So if they have the same law, actually the fact that I have a 0 or a 1 here is not making any difference to generate the law, right? To decide the law of the EG. So if they have the same law, I will prune the branch. And if I realize that actually they have different laws, if I prove that they have different laws, then I keep the branch. Okay, so this is my prune or keep the statistical criterion. Take the set associated to the sequence and comparing the laws. Okay, now is missing to say how we test the laws. So in our example, this is y of 0, 1, 2 and y of 1, 1, 2. So I have here two sets of functions, and I want to test if they have equal or different laws. And this we do it through projective method. How we do it? For each one of these functions, in each one of these sets, I will project them in some random direction. And in order to have some, to satisfy the hypothesis of the method, we need something which is Gaussian. So this random direction has to be Gaussian. This is why we take Brownian motions, for instance, or Brownian bridges. So if I do it for each one of these functions, I project in this Brownian motion, I will have here a set of points, right, in R. And here I will have another set of points in R. So instead of looking at this purple or green piece of functions, I will look at this purple or green points. And then I have now two sets of points on R. And then for these guys, we know how to test law equality, right? For instance, using some Komogorov-Smirnov test. And then what Cuesta D'Alberto co-authors proved in 2006 is if we prove that, if we check, if we apply some statistical test and see that actually these laws are different, so are the original ones, the ones which are not projected. Okay, so this is what we do in order to test this prune or keep criterion that we have, that I'm trying to define to you. Okay. Just to be a little bit formal, this is the way we adapt the Komogorov-Smirnov to the projected sample. So these are the empirical distributions of the projected data. This is the Komogorov-Smirnov distance between these empirical distributions. And this is something that we need when you are applying Komogorov-Smirnov test to samples, okay? And once we have not only, but sometimes you can have three contexts in the same branch and we want to decide to the whole branch. So we have here U, V, and W. So we have more than two to decide, right? To this Komogorov-Smirnov, I just can apply to two samples, and here I have at least three. So we will take the maximum of this statistical all these possible Komogorov-Smirnov distances, okay? And then we apply this criterion. If this maximum is smaller than a branch, then I will just say that everyone here, all these three sets has the same law, and then I will prune. And if I have something which is bigger than C, so at least for one of these pairs, there is a difference in law, so I will keep the branch, okay? Just, okay, some hypotheses in order to make the projective method. We need some conditions on the law of the EG, like Kaleman conditions and continuity. And of course, if I want to check difference in laws in the sets, I need that they have difference, right? Otherwise, I will not be able to apply the statistical test. If we have all this and we have a sample big enough, we can prove that actually we have here a sample that we know which are generating our stimuli, and then we use that to stimulate some volunteer, and then I have here functions, right? And then what we prove is, well, if this tau tree here generated the model, in the end, I will find here, I will estimate here some tau hat, which is the same that with the one which are generating our stimuli, okay? Just a small word about filter. We could apply, for instance, what we have been doing is applying algorithm context and projective method. We could think about other kind of ways of prune and keep branches, right? The only problem is that we are using set of functions, for instance. So we have to have some criteria which can deal with a set of functions. And even though other statistics without the algorithm context, but yet we have to think all the time that actually we are working with functions. So we don't have, for instance, likelihoods. We cannot apply likelihoods for functions. Okay. And these are the main reference. So the mathematical approach, some MATLAB toolbox where you can find all these codes in order to apply these statistical criteria to different kind of data. For functions or not functions, even if you have some finite alphabet as answer, you can find ways of applying this statistical protocol to that. This is available in GitHub freely. And we have also this the results applied at data in this reference, and I believe that Nosny will speak more in more details for you in a few minutes. This is it. Thank you.